In a twist of irony, the moments of explicit symmetry breaking yield the same moments for which humanity itself unites. Within this presentation, we're going to cover the following. Given the integral form Maxwell's equations, we're going to derive the differential form Maxwell Heaviside equations. Then we'll reduce the Maxwell Heaviside equations into vacuum equations and derive the electromagnetic wave equation to calculate the speed of light in a vacuum. Then we'll conduct an experiment to measure the speed of light and increase measurement accuracy across 3 separate trials to see if the experimental values approach the predicted value. Then we'll review the covariant and unified Maxwell's equations, the Maxwell-Lagrangian, the Yang-Mills-Lagrangian, quantum electrodynamics, and then construct the standard model Lagrangian itself. Then we'll derive the semi-classical Einstein field equation, consider the spacetime conformal group SO24 alongside the ADS CFT correspondence, cover grand unified theory, investigate linearized quantum gravity, derive the functional Stokes-Cartan theorem, cover de Rham and Dolbeault cohomology, and finalize with non-commutative geometry. Regardless of your background in mathematics or theoretical physics, I'm sure you'll find something interesting in this video. In part 1A and B, we will be covering things using vector calculus and differential equations. For our experiment, we will rely on no more than basic arithmetic and elementary algebra. And then we'll take off in part 3. We will rely on linear algebra and tensor calculus, exterior calculus and geometric algebra, variational calculus and complex analysis, Lie groups, Lie algebras and functional analysis, differential topology and algebraic topology, as well as non-commutative geometry. Granted, all of this can more or less be summed up under the term differential geometry, so this video can really be utilized as an overview of its applications to physics. Let's cover the integral form Maxwell's equations. We will list them here, starting with number 1, Gauss's law for electricity. To help make sense of these integral-like equations, we'll pull out a notation legend. So E will be our electric field. Epsilon naught in that equation is the vacuum permittivity of free space, and rho is the charge density. So in other words, this double integral over the electric field is proportional to charge density. 2. Gauss's law for magnetism. B here is our magnetic field. That's about the only new term introduced here. Let's continue with Faraday's law. We've introduced a derivative here in respect to time, but no other new terms here are new. So we can continue on to the Ampere-Maxwell law. Mu naught here is vacuum permeability, whereas J is the current density as opposed to the aforementioned charge density that ρ stands for. These four equations contain all of classical electromagnetism in addition to the Lorentz force law. We now want to derive the differential form Maxwell Heaviside equations, and when I refer to the Maxwell Heaviside equations, it's implied that I'm referring to the differential form in this specific context. So we begin with Gauss's law for electricity. So the first thing we want to do is make sure our differentials and integrals are balanced on both sides of the equation, so then we can equate the integrands to form a differential equation. We can use the divergence theorem in this case and convert the left-hand side of the equation into a statement regarding divergence itself. In this case, it's the divergence of the electric field. This model here gives a general idea of what this looks like. So we see here that our integrals and differentials are the same. So this equation holds for any volume. Therefore, the divergence of the electric field is proportional to charge density itself. So charge density is essentially the change of the electric field over space. Now let's consider Gauss's law for magnetism, a much simpler equation, admittedly. We'll apply that divergence theorem once again. So now I've related a boundary integral to a triple integral with a volume. But since we know that both of these are equal to 0, we also know that the divergence integral also goes to 0, and therefore the integrand itself must equal 0, telling us that the divergence of the magnetic field is 0. This is also known as the no magnetic monopole law. If there is a north pole, there is a south pole, and it is the electric field that's doing the work to generate the magnetic field itself, because the magnetic field has no charge and thus is not producing any of the actual work. Now we'll consider Faraday's law. This time we'll apply Stokes' curl theorem as opposed to the divergence theorem. Now that we have an equation relating the electric field to the magnetic field, our structure is a little bit different than our other two equations. Once again, I'll pull out the model, so in this case you can see Stokes' curl theorem in physical form. This total derivative in respect to time, when pushed into the magnetic field of the integrand, becomes a partial derivative in respect to time. This equation holds for any surface sigma, so the integrals and exterior derivatives, or the differentials as we shall call them, cancel on both sides, leaving us with the integrands themselves. So this tells us that the curl of the electric field, or the rotation of the electric field, is proportional to the velocity of the magnetic field itself, exactly minus its velocity. So this tells you if you have an electric field, its curl or rotation, depending on what you want to call it, is the change of the magnetic field over time. Now let's look at Ampere-Maxwell's law. This equation looks a lot more intimidating than the other equations, but it's really not a whole lot worse. We'll once again just pull out Stokes' theorem. And just like that, we already have all of the integrals of the same form and the exact same differentials. So we go ahead and throw in that total derivative. It becomes a partial derivative when acting on the electric field directly. And now the integrands and differentials cancel to give us the following differential equation. This time telling us about the curl of the magnetic field as opposed to the electric field. So the curl of the magnetic field is proportional to current density plus the velocity of the electric field. So these are the four Maxwell-Heaviside equations. The divergence of the electric field is equal to charge density divided by epsilon naught. Whereas the divergence of the magnetic field, on the other hand, is equal to 0. The curl of the electric field is equal to minus the partial derivative of the magnetic field in respect to time, in other words, its velocity. Whereas the curl of the magnetic field is equal to mu naught times current density plus mu naught epsilon naught times the partial derivative of the electric field in respect to time. Now let's switch to a vacuum. When no charge and current densities are present, we have the following vacuum equations. The divergence of the electric field is now equal to 0 since we have no source charges. The divergence of the magnetic field, on the other hand, remains the same. The third equation here for the electric field also remains the same. However, current density disappears in the Ampere-Maxwell law, leaving us only with the change of the electric field related to the curl of the magnetic field. These equations can then be used to easily derive the electromagnetic wave equation for a vacuum. We begin by deriving the equation of motion for the electric field. We notice, however, that the electric and magnetic fields are coupled in two of the four vacuum equations, namely the third and fourth ones we discussed prior. Due to the nature of curl as opposed to divergence, we're still left with a system of coupled partial differential equations. Their symmetries can and will be exploited, however. So let's go ahead and start by considering the third vacuum equation, showing us the curl of the electric field. This equation can be decoupled by taking its curl. On the right-hand side, we can go ahead and take out that partial derivative and place the spatial derivative, which in this case is that gradient operator, and we go ahead and just take the cross product of that gradient operator and act on the magnetic field directly. So we now have minus the partial derivative of the curl of the magnetic field. And we know what the curl of the magnetic field is because that's the fourth Maxwell equation. So now we have the electric field on both sides of the equation. We can go ahead and distribute that partial derivative in to create an acceleration derivative, in that case, a second partial derivative in respect to time. That gives us the acceleration of the electric field. We can then take note of the common theorem from vector calculus to make it second order on both sides of the equation. And this is given to us by the Laplace operator acting on a vector field. That converts this to a second order equation on both sides. Now all we have to do is perform some basic algebra to get the wave equation for the electric field itself. The divergence of the electric field in a vacuum, of course there being no source charges, goes to 0. And since we have negation on both sides of the equation, we can cancel that. This is now the wave equation for the electric field. And it just so happens that we can replace E with B, and the same equation then holds true for the magnetic field. So the Laplacian, in other words, the sum of second derivatives in respect to spatial coordinates of the magnetic field, is proportional to its acceleration. These are the equations of motion for electric and magnetic fields. Combined, we have the motion of the electromagnetic field in a vacuum. We'll expand that Laplacian so you can see its full structure. We can use this equation to calculate the speed of light in a vacuum. First, we compare this equation to the general wave equation, where v is the phase velocity of the wave. Ignoring the fact that we just have a placeholder vector field here, the only actual difference between these two equations are the representation of the constant itself, 1 over v squared, which must be related to the electromagnetic wave equations mu naught epsilon naught. So therefore v squared is equal to 1 over mu naught epsilon naught. To then obtain the velocity, all we must do is take the square root on both sides of the equation to find that the velocity of the electromagnetic field itself is 1 over the square root of mu naught epsilon naught. Mu naught epsilon naught are well-defined constants. So when we combine these together, we get the following decent-sized equation. However, this simplifies. We can use a calculator to pull this off. We get an exact velocity of 299,792,458 meters per second. This is also called the speed of light. For those wanting different units, especially those in homeland America, the speed of light in a vacuum is nearly 700 million miles per hour, which is about 1 billion feet every second. Granted, this really doesn't help you visualize this, but this wave can travel around the world about 7 or 8 times every single second. We wanted to think of a way to approximate this number by a physical experiment that we can conduct safely at home. Most people already have devices in their homes that produce measurable electromagnetic waves, but one device in particular makes it rather trivial to approximate the speed of light up to a few significant digits. We know by theory that any electromagnetic wave in vacuum should travel at precisely speed c. So electromagnetic waves generated by a microwave oven should be sufficiently close to this speed. We can remove the tray of the microwave oven or disable the rotation feature. Then we place a large, flat block of either marshmallow or chocolate in the microwave oven. We know, again by theory, that the electromagnetic wave should take particular shapes at different energies. And by changing the frequency and wavelength of the wave, different spots on the food should burn depending on where the antinodes of the wave are located relative to the food. Of course, the military has already taken advantage of this fact. Essentially, we need an equation that relates the velocity of the wave to its wavelength and frequency. Of course, that's the fact that velocity is equal to wavelength times frequency. How convenient. Let's go ahead and try a first approximation to get the speed of light, or get as close as we can to it. So we begin by microwaving a chocolate bar in the microwave oven while the rotating tray is removed. We notice the following pattern forming across the bar, where it appears as if the chocolate bar itself is melting into the shape of the electromagnetic wave that we saw earlier. Of course, we could just say this is entirely coincidental. We notice that the crests are roughly 6 centimeters apart. Recalling the image from earlier, we know the full wavelength must be twice this number. If we can use this information to somehow reproduce the speed of light, I would say that's probably less than coincidental. So we obtain a wavelength of approximately 12 centimeters. Converting to the formal SI unit of length, which is meters, we get 0.12 meters. So now we have a value for lambda. Now we just have to find out our value for f, the frequency. That's much easier to figure out, however. Just look at the RF output frequency listed on the back of the microwave oven. For reference, the common target frequency is 2,450 megahertz. The formal SI unit for frequency is hertz. And so 2,450 megahertz is 2.45 gigahertz, which is 2.45 billion cycles per second. So we obtain a frequency of 2,450,000,000 hertz. We'll use scientific notation for that, of course. We obtain the following result in terms of meters per second. And writing this out explicitly, we obtain exactly 294 million meters per second. Not that far away from the speed of light, and it's about roughly 98% that speed. Let's try a second approximation with a more accurate measurement. So with velocity 1, we got 294 million meters per second, when the true velocity should be 299,792,458 meters per second exactly. So after taking an average of measurements and taking more time with our roller, we get a wavelength of 12.2 centimeters, a little bit more precise, and that's 0.122 meters. This gets us even closer to the true speed predicted by theory. This gets us to 298,900,000 meters per second. That's roughly 99.7% the way there. Let's give a third approximation. We can be more precise by using the International Convention for the Wavelength of the Microwave Oven's standing wave, which is about 12.23 centimeters, converting to 0.1223 meters. This is even more precise than what we gained from our second approximation method that relied on repeat trials. Let's just kind of cheat here and just take the information right from the manufacturer. This is still something we can perform at home. This gives us 299,635,000 meters per second. Compare that to our speed of light. We're very, very, very close now. Approximately 99.9 or so percent the way there. With our third approximation technique, we have reached an accuracy of 3 significant digits, which is an exceptional degree of accuracy for an experiment that can be conducted at home. So a clear pattern has emerged. We're very obviously approaching the true speed of light. Our theory seems to be correct. And now it's time to get into the advanced topics and go all the way to summarizing essentially the entirety of theoretical physics. We're going to be covering advanced electromagnetism here, quantum field theory, general relativity, and finish off with quantum gravity and beyond. First, let's consider the covariant Maxwell's equations. We can summarize the four Maxwell Heaviside equations into two equations. One which represents the homogeneous equations, which are Gauss's law for magnetism and Faraday's law, respectively. The others representing the inhomogeneous equations, Gauss's law for electricity and Ampere-Maxwell's law. So these four equations can become two. There are two fields of math we will use to demonstrate examples of how this can be done, but there will be a third field introduced that is capable of summarizing all four equations into a single, unified equation. So we will look at Maxwell's equations from the perspective of the following three areas of mathematics. We'll consider it in tensor calculus, as well as in an exterior calculus, and then geometric algebra. So first, we'll consider tensor algebra, or in other words, the arena of tensor product spaces. We begin by combining the electric and magnetic field components into the components of a rank 2 tensor called the electromagnetic field tensor, otherwise known as the Faraday tensor. There are four primary variations we care about. Two are formed by the covariant and contravariant Faraday tensors, and the other two are formed by the tensors existing in their dual spaces, which are dual tensors. We will first consider the covariant and contravariant Faraday tensor components defined in terms of a 4 potential. These will be our two tensor equations from which the rest of electromagnetism shall fall out. The right-hand side of these equations yield the following matrices. Interesting structure here, especially with zeros all the way down the diagonal. But what happens when we multiply this covariant and contravariant tensor together? We get 2 times the squared magnetic field minus the squared electric field. We can compose the dual tensor components by transforming electric field components into magnetic field components and then transforming magnetic field components into negative electric field components. Reversely, we could have also instead just changed electric field components into negative magnetic field components and then changed positive magnetic field components into positive electric field components. That would have produced the similar structure Remember, it's not what the words say on the screen that matter, it's the structure and logic that holds it together that makes mathematics hold true. To obtain the two inhomogeneous equations in the form of a single covariant equation, we take the covariant derivative of the contravariant Faraday tensor. Let's go ahead and distribute that partial sub nu and rearrange. Partial sub nu with a sub nu cancel out. This gives us a source term. In terms of the D'Alembert operator, nonetheless. So we know this must be our source term, and we can write this in terms of the current density, J. To obtain the two homogeneous equations in the form of a single covariant equation, we take the covariant derivative of the contravariant Faraday dual tensor, where in this case I will go ahead and distribute the partial derivative sub mu into the right-hand side of the equation in the parentheses. This four-dimensional Levi-Civita tensor density cancels with mu, sigma, and lambda due to Einstein's summation convention. So of course we just get 0 then. And this can actually be intuited from the transformation of e to b and b to negative e, which defined our dual transformation earlier, meaning we don't even need to recognize the connection with the tensor density that I described above. When applying these transformations to the inhomogeneous equations, we obtain the homogeneous equations that already equal 0. With that in mind, we are immediately endowed with the foresight that if the covariant derivative of a contravariant Faraday tensor is non-zero, then the covariant derivative of its dual must be 0. From the perspective of tensor product spaces, we see that Maxwell's 4 equations can be condensed into 2 equations that are not only compatible with special relativity like the original 4 equations already were, but now also coordinate independent. And this is all of electromagnetism condensed into 2 equations. This means that these equations describe a fundamental behavior in nature that is mathematically rich in structure, but yet also holds true regardless of the coordinate system agreed upon. Though these equations are essentially the same as the original 4, the covariance of these equations establishes a technically stronger and more fundamental statement than the original equations did. It tells us, for example, that it's the structure of space-time itself that enforces and guarantees electromagnetic dynamics without failure. Now let's consider these covariant equations in terms of exterior product spaces. So from that perspective, we focus on the following fact about what we call now the Faraday 2 form. In the Faraday 2 form is an element of the second exterior power of the dual energy momentum tensor on a manifold. So T star is that dual energy momentum tensor, and M resembles a 4-dimensional Lorentzian space-time manifold composed of differential 1 forms dt, dx, dy, and dz. We expand F as a differential 2 form. And now we do the same thing for the magnetic field. So we have the electric components in terms of a differential 2 form, so dt wedge dx creates a differential volume element in terms of one spatial coordinate and one temporal coordinate. That's just an example. If I was to flip dt with dx, that would give us a positive dx wedge dt. So they're anti-commutative, as I was saying. In the prior method of tensor calculus, we relied on covariant derivatives of the Faraday tensor and dual tensor components. In exterior calculus, however, we will instead take exterior derivatives of the filled two forms themselves, and the exterior derivative of a differential k form then generates a differential k plus 1 form by definition. So now we have two wedge products combining three differential 1 forms into a differential 3 form. So these are all our electric field components here, and now we have to do the same for the magnetic field components. Pretty hefty equation, but we'll see as this cancels out really nicely. So let's go ahead and organize that. And then our last term here. These last three terms automatically cancel out here in subtraction. And this top term just gives us the divergence of the magnetic field itself. And that's always equal to 0. So the exterior derivative of the Faraday 2 form is 0. We know now that it must be the exterior derivative of the dual 2 form that yields the current density. So the exterior derivative of the Faraday 2 form equals J, as long as the Faraday 2 form is in its dual stage. From the perspective of exterior product spaces, we see that Maxwell-Heaviside's four equations can once again be condensed into two covariant equations that give the same laws of physics in all coordinate systems. And they look even simpler now than they did before. And as an interesting aside, let's first consider the Maxwell-Lagrangian. In mathematical gauge theory, the stationary action can be expressed as an inner product of the fields themselves. And so then the integrand with this factor of minus 1/2 gives us the Lagrangian. So the kinetic minus potential energy is negative 1/2 times the Faraday 2 form wedge its dual. In a vacuum, we can ignore charge densities and expand our Lagrangian back in terms of tensor components as follows. We know what F sub mu nu and F upper mu nu equal because we showed that earlier. That's 2 times the squared magnetic field minus the squared electric field. So let's go ahead and plug that in. This now tells us that the vacuum Lagrangian is negative 1/2 b squared minus e squared. We obtain the Hamiltonian by changing the negation between the fields to an addition. This gives the total energy of the electromagnetic vacuum. Now let's look at a geometric algebraic space. We recall that Maxwell's equations are essentially a collection of curl and divergence equations. So we can imagine if we had some sort of operation that, say, combined curl and divergence in a 4D space-time, we could combine Maxwell's equations into a single unified covariant equation. A certain geometric algebra, as it turns out, describes the fundamental algebra of spacetime itself, and it's a Clifford algebra called CL13R, though CL31R is also a valid choice depending on Lorentzian metric signature. It is worth noting that expanding either algebra to CL13C or CL31C which is what we call complexification of the algebra, we then derive the Dirac algebra, where spinor representations arise for quantum theory. And indeed, vectors can be decomposed into tensor products of spinors. And these fundamental and irreducible representations that are a part of these tensor products are called Weil spinors, which are the building blocks in quantum theory for all the other spinors, such as Dirac spinors and Majorana spinors, that we later see crop up in quantum field theory. We first consider the geometric product decomposition property, which is part of the definition of a geometric product. So the geometric product of vectors A and B, or multivectors in this case, A and B, equals the inner product plus its outer product. Notice that this property of the geometric product combines an inner product with an outer product, as I just stated, so this must be the key to unifying Maxwell's equations. This means the geometric product of the gradient operator with a bivector, such as f, yields the properties of divergence and curl of f in a unified framework. This then is called the space-time derivative of a vector field f. So the dot product and curl are just byproducts, they're just limiting cases of this much more general statement. Due to the structure of Maxwell's equations in spacetime itself, the definition of the geometric product decomposition of the gradient operator acting upon a bivector automatically yields electromagnetism. Since both the divergence and curl of the electromagnetic field are unified in this equation, it must equal a current density when not in vacuum. So the spacetime derivative of f is equal to current density. And just like that, you're looking at the entirety of electromagnetism in one equation. Isn't it just fascinating that the entirety of electromagnetism amounts to the definition of a spacetime derivative acting on a bivector? Under complexification with the Dirac algebra, this theory then converts naturally into the study of quantum electrodynamics, and the above equation can then even be interpreted as a Cauchy-Riemann equation for spacetime and complex analysis. In quantum field theory, the invariance of the electromagnetic wave function establishes a unitary U1 gauge symmetry, which, when considering high-energy theories such as this standard model, couples with a special unitary matrix with it. These have a determinant of 1, a trace of 0, so SU2 to form the electroweak gauge group SU2 cross U1. The fact that the electromagnetic wave obeys this commutative U1 symmetry implies that the quantum electromagnetic field experiences linear superposition, where waves or photons can coexist or quote-unquote overlap within the same state. Zero mass, zero charge, spin 1. It is the only particle that's exactly like this, that is also a vector boson. This immediately tells us that the electromagnetic field is a gauge boson field obeying Bose-Einstein statistics. As a result, photons must be the generators of force in electrodynamics. In-particle photon states can then be modeled by the following symmetric tensor product Fock space. S plus is our grading operator for commutativity and anti-commutativity. So S plus, if we have a plus there, we're referring to commutativity. If it was a minus, we'd be referring to explicitly anti-commutativity. And if we had some type of letter here to switch between, this combines both of those structures. So we're only looking at the symmetric tensor part in this case, because photons can interact in the same locations, the exact same state. We can form Bose-Einstein condensates nowadays with this information. We can expand that as follows, starting off with C, which is the set of complex numbers. That establishes the vacuum state, because these are just, you could think of an infinite amount of possible coefficients you can multiply into nothing and you still get 0. So the complex numbers themselves are a ground state for our complex Hilbert space. And then H is a single particle state with all the degrees of freedom, potentially infinitely many if we need it to be, in this one space. And that will resemble everything that one particle can do in that space. And then we have the S plus operator, which grades us to ensure that when we multiply two of these photon spaces, these symmetric Fock spaces, they can overlap with one another to produce Bose-Einstein statistics. So therefore, H sub 1 cross H sub 2 is equal to the tensor product of H sub 2 with H sub 1. It doesn't matter which way you organize them, they're symmetric either way. That's what makes it a force carrier, by the way, separate from, say, like an electron that's just a matter that then fills the force of the photon. So now let's look at the electromagnetic wave equation from a geometric algebraic perspective. So we'll take a look at the vacuum case in the specific instance with the space-time derivative acting on our 2 form. The electromagnetic 2 form can be expressed in terms of the outer product of the electromagnetic potential with the 4 gradient. We can we can call this a bivector if we want to. If we want to be a little bit more specific in the terms of geometric algebra, we would often call this a bivector and not necessarily a 2 form, but we know what we're talking about here. It's a form of dimension rank 2 here, so let's just think of it that way. All we have to do now is place this value into the equation. And it's the same equation, we're just representing F with a different notation. So in other words, the vacuum geometric algebraic equation is already the electromagnetic field equation. That just gives us the D'Alembert operator acting on a potential. So we see that the electromagnetic field we have been measuring all along is just the self-propagation of electromagnetic potential across spacetime. In vacuum, all observers will then agree on the speed of this propagation. This is related to the fundamental principles of special relativity as a consequence of that aforementioned structure of spacetime I mentioned. A quick connection with complex analysis is worth considering too. Again, let's bring back a vacuum equation. And let's consider a 2-dimensional case. So the general solution to this Cauchy spacetime equation is really what it is for a 2-dimensional electromagnetic plane wave in vacuum is obtained by method of a Green's function, which we will denote g of z and s. It acts then as the kernel of an integral. G of z and s yields a shifted Dirac distribution when we apply the D'Alembert operator, recalling that the Dirac distribution is not a function, it's a functional, it's a generalized function. So D'Alembert operator g of z and s is equal to the Dirac delta distribution of z minus s. The general solution turns out to be Cauchy's integral formula of complex analysis itself. So f of s is equal to 1 over 2 pi I times this contour integral of f of z over z minus s, all in respect to z. Now let's consider non-abelian Yang-Mills theory, which is more or less a generalization of Maxwell theory. The mathematical theory behind Maxwell-Lagrangian dynamics is generalized by Yang-Mills theory, which envelops U1 as a subgroup of a greater class of generally non-abelian groups. Now remember, U1 is commutative, so the algebraic structure is what we call abelian. However, the greater class of Yang-Mills theory generates these groups and structures that are generally non-abelian, so we have non-commutativity as we discussed. The most important Yang-Mills group for which U1 is a subgroup is the Lie group of the Standard Model of Particle Physics, and it's a manifold called capital G with a tangent space T sub I of m at this manifold's identity called a Lie algebra, little g. So G is equal to the cross product Lie group SU3 cross SU2 cross U1. And its corresponding Lie algebra at its tangent space at identity is then SU3 plus SU2 plus U1 as a direct sum. Under U1 alone, the Yang-Mills Lagrangian reduces to the Maxwell Lagrangian we already know. So all of electromagnetism, as far as we understand it in the classical theory here, is just a byproduct of this one U1 subgroup of SU3 cross SU2 cross U1. Under the full group, however, we obtain the complete Yang-Mills Lagrangian. Now let's see what these tensors are made up of. The Yang-Mills Lagrangian is a Lagrangian density that describes gauge fields that mediate forces within our quantum field theories. So in other words, these are not spinors, these are integer spin particles, similar to our photon. It is composed of the sum between the electroweak gauge field for electroweak bosons and the strong nuclear gauge field for gluons that hold our quarks together inside of atoms. So your electroweak bosons are going to be your bosons that lead up to your W plus, W minus, and Z bosons, as well as your photons. That's where your electroweak bosons come into play, and then the remaining strong boson is the gluon itself, and that gives you strong nuclear fields. So you can see this Lagrangian density split up into two further Lagrangian densities of the W and B and G bosons. And we can expand that, of course, further in tensorial notation, as you see here. We will see later that the SU2 cross U1 group undergoes symmetry breaking from the Higgs mechanism. When this happens, W plus N minus bosons emerge from the previously combined W1 and W2 fields. Z bosons and photons emerge from the previously combined W3 and B0 fields. The ones that obtain no mass from the symmetry breaking are what we call photons. Those things that were once similar to these photons that do end up gaining mass are what we call Z bosons. So just like the photons, they continue not having charge, but they end up having mass. So a Z boson is basically a massive photon in a very specific context. And it's not after this whole symmetry breaking process that electromagnetism and the weak nuclear forces are even distinct forces, whereas, for example, light can exist independently from what you might call any other particle or force. In quantum electrodynamics, we are interested in how the electromagnetic field interacts with fermion fields, spinor fields, which is described by photons interacting with fermions such as electrons. The following Feynman diagram describes a fundamental interaction that is allowed within the symmetry constraints imposed by the Poincare group. So follow the arrows. We can read this from right to left if we wish to. And in that case, what you're actually witnessing are two particles, two electrons in this case, coming closer and closer to each other, sharing a photon, a symmetric photon. So you have two anti-commutative product spaces merging together. A commutative product space interacts between those two, cancel out to give a spin 1 total behavior, and then these two spin 2 atoms now experience what we call repulsion. It's just a result of the symmetry. There's nothing necessarily physical that we have to explain to understand why repulsion occurs here. It is just a logical inevitability when we think of how these things commute with each other. We could just read this chart left to right too and say, oh no, actually these are not electrons going right to the left, as far as if we imagine time going right to left, we can see this as time going left to right, and instead these are like antiparticles that are now repelling off of each other and going another direction. So that's another way we can read this. So in the middle there, you have the squiggly line of photon, and then you have the electrons meeting and then interacting with that squiggly line, and that interaction vertex, that's where they experience repulsion. Electrons and positrons, which are just anti-electrons, obey Fermi-Dirac statistics. That's the repulsion I'm talking about. In-particle electron states can then be modeled by the following exterior product space, and this will explain why they repel. It's because in this specific grading, I don't use an S- acting on a tensor product, because when I use the wedge product, it's already assumed that I'm talking about an entirely specifically anti-symmetric tensor product. So then h sub 1 wedge h sub 2 we already know is equal to negative h sub 2 wedge h sub 1. These particles cannot occupy the same state. They just can't do it. It's mathematically impossible. Since electrons cannot coexist in the same state, they experience repulsion as a result of Pauli's exclusion principle. This tells us that electrons and positrons must be the matter particles that experience the force that I just mentioned, caused by the tensor product space of photons. The infinitely many symmetries that can form from collisions of these tensor and exterior product space ensembles of discrete states are Lie group isometries. In the real universe, we just say, oh, these are particles interacting. But really, this just yields the essence of physical chemistry in our universe, but in a sense that we can mathematically model it. So you think about the wave function of the hydrogen atom and all the different states that the probability density plot can take. That's given by the fact that you have discrete integer states that these electrons can take in an orbital of an atom. So if you had to balance your chemistry equations, now you know quantum mechanics is to blame. I mean, think about just the shape of the electromagnetic wave down to just the shape of a DNA molecule. All the forces that you experience, if your hand is not going through the floor, if gravity is not automatically pulling you into a black hole, if the entire Earth is not automatically just this black hole that's being, all the electromagnetic forces being ignored, it's because we have this anti-commutative tensor product space dictating interactivity between particles. So symmetry interacts between non-symmetry to create a mixture of this nonlinear reality that we consider all complex and unified. Now let's consider the Dirac equation, which basically yields us a tensor space of quantum spin algebras. And it's indeed a covariant form of the Schrödinger equation, generalized to spacetime. With this slash, we're using Feynman slash notation. But we'll go ahead and distribute the psi into this, which is just our fermion wave function. Expand the Dirac notation by showing that the Feynman slash operator is really just the gamma matrices with the partial derivative. And so with that being said, we should probably define what these gamma matrices are. So really they're 4x4 matrices, but I've condensed them into this notation. So I sub 2 is really defined by what I'm going to show on the right here, the polysigma matrix, sigma 0, and that's going to be the identity matrix. And that's I sub 2 because it's a two-dimensional identity matrix. So you can see how now when you apply that I sub 2 and the negative I sub 2 over here on the left, the Dirac gamma matrices are actually 4x4 matrices for space-time itself. So now we're going to give the X, Y, and Z Dirac gamma matrices defined in terms of the polysigma matrices. And yes, indeed, these are all rotation matrices that make up Lie groups. We can look at their commutativity rules. The Dirac gamma matrices with their commutation relation gives us 16 basis elements in CL13, whereas in polysigma matrices we end up with 8 basis elements in CL03 as a result of the commutation relation. A lot of times people write this in natural units, so the C and the H bar disappear, and then we can drag this all into a zero equation, essentially, making it look all nice and pretty. So a lot of people might see the Dirac equation written like this below. We can multiply any two sigma matrices as follows. This gives us something in terms of the Kronecker delta function in the identity matrix, plus this imaginary number acting on this three-dimensional Levi-Civita tensor density. But we can expand that in terms of the inner product and a cross product. And when I multiplies into the cross product, that actually ends up turning into the definition of a wedge product. So basically we just took Euler's identity and made up the definition of the geometric product right from scratch, like almost for free, just by considering what it means to multiply two sigma matrices. And so when I said this produces basis elements in a Clifford algebra, it should make sense now. This gives us a definition of the geometric product in terms of Euler's formula, since the dot product relates to the cosine function and the cross product relates to the sine function. So cosine theta plus I sine theta is, of course, e to the I theta. That's Euler's formula. The geometric product, then, is a type of exponential function. A similar process then holds for gamma matrices. So in other words, you can extend Euler's identity and formula into a space-time equation in terms of Clifford algebra. Now let's consider the quantum electrodynamic Lagrangian. To obtain the Dirac Lagrangian from the Dirac equation, all we have to do is multiply the equation by a conjugate spinor field. The quantum electrodynamic Lagrangian density describing the fermion and electromagnetic fields as free fields can be obtained by adding the Maxwell Lagrangian to the Dirac Lagrangian. This specific density function is then arguably the most famous representation and is even often called the QED Lagrangian. The full QED Lagrangian, however, includes gauge fixing, interaction terms, and sometimes even others, though at the cost of complexity. This makes it a less famous, though more useful, rigorous, and general representation. Now let's head towards the standard model of particle physics. The Lagrangian density formed by the Dirac and Maxwell terms with the addition of a gauge parameter and the Faddeev-Popov-Gauss Lagrangian, which is what we'll use to cancel gauge anomalies, is given by the following density. By extending the associated Yang-Mills gauge group to SU2 cross U1, we obtain the electroweak sector of the standard model. This also includes the Higgs mechanism. But by adding the additional term for gluons for the strong nuclear force found within the full Yang-Mills Lagrangian shown earlier, which is SU3 cross SU2 cross U1, we obtain the true Lagrangian for the standard model of particle physics. When SU2 cross U1 splits into distinct Lie groups SU2 and U1, the electroweak gauge group undergoes spontaneous symmetry breaking, as we call it. A self-interacting scalar field experiences a sudden shift in potential energy. Electrons, quarks, W+ bosons, and Z bosons are endowed with fundamental mass as they experience a resistance against their default speed of c in a vacuum. This is called the Higgs mechanism. Due to this, a spacetime with gravity, electromagnetism, and two distinct nuclear forces is established. Here's an expanded Lagrangian of the standard model, a little bit different from the form that we took, considering I'm using different gauge terms and whatnot, but you can still get the general idea. This was made many months ago before this video was even planned. So you can see all the particles, bosons and fermions, the interactions, and everything in between here in explicit form. Now we want all of known physics in a single Lagrangian. By including the Einstein-Hilbert Lagrangian in the standard model Lagrangian density, we have an equation expressing essentially all known fundamental principles of physics, detailing an apple falling off a tree and the quantum field fluctuations that make up that apple, to the collision of black holes and space-time expansion itself, though it's still not a theory of quantum gravity itself, and admittedly lacks things like dark matter, but we'll call this a universal Lagrangian because it contains all of the known laws of physics in our universe. So we have the standard model as expected, but now we have the Einstein-Hilbert Lagrangian added on. And we've converted from 8 pi g divided by c to the third power into h bar divided by 16 pi times what's called the squared Planck length, which I write a sub p for Planck area. So we know we're going to want to quantize gravity as we move forward. It's kind of like the whole deal that everyone wants to worry about. So I go ahead and just write this down in terms of the Planck scale. We can compactify the universal Lagrangian as well. What we've formulated is a Dirac, Yang, Mills, Yukawa, Higgs, Faddeev, Popov, Einstein, Hilbert Lagrangian that describes all known fundamental laws of physics, and it's the simplest form that it can take right here. So the universal Lagrangian is just the sum of the standard model and the Einstein-Hilbert Lagrangian. To obtain the field equations of motion for whichever aspect of physics desired, simply choose a Lagrangian even within the Lagrangian densities and plug one or many or all of them into the covariant Euler-Lagrange field equation, which is essentially just taking the functional derivative of a Lagrangian in respect to a particular field, or a metric. So we can obtain general relativity from quantum fields, and that's how we get the semi-classical Einstein field equation. We can use the Much like the universal Lagrangian, the semi-classical Einstein field equation encapsulates all known fundamental laws of physics. It expresses that it is ultimately the act of quantum fields that yields the energy momentum for which relativistic gravitational dynamics is made apparent within our universe. We begin by considering the Einstein-Hilbert action, where the Standard Model defines the matter Lagrangian density of the stationary action. I didn't mention this prior, but you see the g under that square root? That's the determinant of the metric tensor. To solve the integral, we plug the integrand into the covariant Euler-Lagrange field equation, which amounts to taking its functional derivative in respect to the metric, otherwise known as the gravitational field. This gives us the following gauge-invariant, nonlinear covariant functional differential field equation of second order, which is the semi-classical Einstein equation. And we can rewrite this simply as follows by taking out that functional derivative. And we'll just demonstrate that it gives the familiar looking Einstein field equation here. We'll just show what these functional derivatives equal. So the functional derivative of square root of negative g acting on the Ricci scalar gives the Einstein tensor, which the Einstein tensor is just the Ricci tensor minus 1/2 the Ricci scalar times a metric tensor. So when you vary the cosmological constant in respect to the metric tensor, and you multiply it by square root negative g and the scalar 2, you just get back the cosmological constant and a corresponding metric tensor. When you do the same thing to the Lagrangian of the Standard Model, you get the expectation value of energy momentum. By bringing back the Einstein-Planck constant to the other side of the equation, we have the semi-classical Einstein field equation. We can condense that constant. We'll call it the Einstein-Planck constant. On the left here, we see a picture, or a simulation rather, of a quasar, reduced light for clarity of course. It's a simulation of a 60 billion solar mass black hole, the accretion disk more particularly, with relativistic jets viewed from a distance of 5 light years away. And here's a picture of a wormhole, which is also, of course, a solution to this equation as well as the original classical equation. When we write it in explicit tensorial form and not just component form, we get that the Einstein tensor plus the tensor that deals with cosmological expansion is equal to the Einstein-Planck constant times the expectation value of energy momentum. The energy momentum tensor components T sub mu nu for the Standard Model are given by the sum of the following Dirac, Yang-Mills, and Higgs energy tensors. So there's your Dirac energy momentum tensor. Now here's the Yang-Mills energy momentum tensor. And then finally the Higgs energy momentum tensor. T sub mu nu in the semi-classical Einstein field equation is then just the sum of these three energy momentum tensors. And it is these three energy momentum tensors that collectively contribute to what we call gravity and curvature in space-time. It is the energy from which space itself curves. Something interesting happens when we consider the time component of the energy-momentum tensor in a fluctuating quantum vacuum. We can expand this as an integral. And then we can even write this as a Feynman path integral. The time component of the energy momentum tensor can be attained by multiplying the expectation value of energy density ρ by the tensor product of velocity 4 vector time components u sub 0, or u naught. And u naught is just the time component of the 4 vector, which is the speed of light in this case. So we gain the following multiplication, which just gives us a 4x4 matrix. But there's only one component, of course, the time component, which is the upper left corner where we have t on the top and then t on the left, so we get a pure time component, c squared, 0 is elsewhere, so we just get a generalization of E equals mc squared. The expectation value of the time component of energy momentum yields a generalized relativistic principle of mass-energy equivalence. In simpler terms, as I mentioned, this generalizes E equals mc squared. For those confused as to why mass density and Einstein's mass-energy equivalence shows up in a vacuum, recall that we're working with the quantum vacuum. This means that there are constant fluctuations of energy as a result of Heisenberg's uncertainty principle. This results in small amounts of space-time curvature and propagations of gravitational waves. Here's a 9-year map of thermal fluctuations in the cosmic microwave background. Credit to NASA and the WMAP science team. This is the earliest light that we can see in the universe, telling us the fundamental structure of its earliest stages. To summarize, there are a handful of elegant ways in which we can express all known fundamental laws of physics in a single equation, and I have shown 2 examples in this presentation. That is, of course, just the Lagrangian, the universal Lagrangian we developed, and then the semi-classical Einstein field equation. It would seem then that all of this is a consequence of a much simpler equation that comes from the calculus of variations, and that was just the exterior derivative. In this case, the variation of the stationary action always equals 0. So in other words, this is the ultimate consequence of the fact that there's no such thing as magic in the universe. That means energy doesn't just magically exist. There either never was energy or there always was, or that means the same thing. There was never just, oh, there's nothing, oh, there's something. Like, that's not what this equation is telling us. What's saying is everything happens because it just is a possibility that it can happen, and therefore it takes absolutely no energy for all of it to happen, if it can happen. That's what this is saying. It's the principle of least action. Nothing is actually being put in. There's no effort. Nothing's being extracted from anywhere else to make everything happen. And so really, it's like saying you could have an entire universe where the net sum of energy is 0. And you basically, it's like saying from a global perspective, it's like you don't have a universe. But locally you do, because you have these symmetry breaking constructs where things are being warped and curved. And so you point over there, there's some energy, and that's different from pointing that direction where there might not be energy. But overall, it cancels out. So you can have matter and antimatter canceling out. You can form whatever you want out of pure probability, essentially. And there's nothing magical about it whatsoever. That's the principle of least action. It tells you that a universe is guaranteed to happen if there is a potential for any level of energy to already have existed. That's what it tells you. In a 4D spacetime, the largest group that the non-zero Maxwell equation is invariant under is the Poincare group ISO 13, assuming we're using a Lorentzian metric signature of 13, where a non-zero equation implies the presence of a current and charge density, of course. Interactions of current densities introduce characteristic lengths, limiting the possible transformations that leave the system invariant. So if I have characteristic lengths, I no longer have a length invariant system where, for example, I can scale something up and have the exact same angles, all the different same because now I have to actually focus in on a particular value that must be obeyed under all frames of references. But in this case, under a vacuum equation, we have conformal invariance. There's no characteristic lengths because there's no currents. There's no charges present. And it's for this reason that the vacuum equation is particularly fascinating. By eliminating the presence of electric charges in space-time, it becomes invariant under a wider span of symmetries, which in this case we call conformal invariance. The conformal group of space-time is called SO24. It contains not only the Lorentz group of transformations as well as the translations that are present within the Poincare group, but it extends the range of symmetries to dilations, angle-preserving conformal transformations, parity transformations, and time reversal. SO24 is the largest group for which Maxwell's vacuum equation is invariant. And it means that electromagnetic fields in a vacuum are, of course, conformally invariant. And I know I'm kind of re-emphasizing this in multiple different ways, but it just kind of implies that these electromagnetic fields are, it's almost like saying fundamental is an understatement for these things. Like, everything that comes from that seems fundamental. These are more than that. They continue to hold for degrees of freedom that are nonsensical in our current space-time in our universe. I mean, rules can completely change, and electromagnetism will act in a certain way to where our universe can be a byproduct that completely agrees with how the electromagnetic form was in the prior state, in a higher sense of freedom. And then, like, the electromagnetism of our universe could be just like a source-based subset of that vacuum isometry state. The conformal covariance of the vacuum equation reinforces that the speed of light in a vacuum will be constant for all observers. SO24 is also known as the isometry group of five-dimensional anti-de Sitter space, ADS5. This makes it a major group of interest in the study of ADS-CFT correspondence. We first consider an isomorphism to motivate our interest. That is, that SO24 is isomorphic to SU22, a real representation being represented by a complex representation. The ADS-CFT correspondence is ultimately the name given to the Maldacena duality conjecture, which we see described here by the Syracuse University Department of Physics, and then explained over here by myself on the left. It states that an n-dimensional gravitational or string-based theory can be calculated by an n-1 dimensional conformal quantum field theory existing on the boundary, and vice versa. So everyone says, oh, you have to have string theory. Nonsense. It just means they haven't studied the math for the sake of the math. A consequence of the isomorphism shown prior is that a gravitational or string theory existing in an ADS5 spacetime obeying the SO24 conformal isometry group can be calculated by a conformal field theory in a 4D spacetime obeying SU22. This is also to say that a field theory existing in a real vector space may also be more easily calculated by a dual theory existing in a complex Hilbert space of one less dimension. This is an example of holographic duality, where a theory existing in the bulk may be analyzed by a theory existing on the boundary enveloping that bulk. Consider, for example, how this may relate the surface of an evaporating black hole to its degenerating volume. This latter example leads to an ADS black hole correspondence, helping to simplify calculations in the study of black hole thermodynamics as it relates to the differential geometry of the black hole itself. And real quickly, we'll consider the Bekenstein-Hawking entropy formula in black hole thermodynamics. Though derived long before the ADS-CFT correspondence was discovered or even conceived in any type of way, the formula for black hole entropy is among the primary results that are agreed upon and yielded by many theories that utilize the correspondence anyway. It relates the entropy of a black hole to its surface area. This means the entropy of a black hole is encoded on its event horizon. That's step one of what we need to realize to understand a connection with the correspondence. Okay, so this implies that a black hole has a temperature. This is given by Hawking's legendary equation, showing that the temperature of a black hole is inversely proportional to its mass. So a black hole cools down as it gains mass energy, meaning it heats up as it loses mass energy. It is thus implied that a black hole must emit radiation when the size of the event horizon decreases. This is called Hawking radiation. It is, of course, within such study that we see an intersection of quantum field theory, thermodynamics, and general relativity. Let's quickly take the simply connected Lie group, the universal double cover of SO24. It should be mentioned that the double cover of SO24 is spin 2,4. Let phi be a 2-to-1 homomorphism. Dual mapping spin 2,4 with SO24. In simple terms, one element of SO24 corresponds to two elements of spin 2,4. In more specific terms, spin 2,4 is a surjective domain that maps twice onto the codomain of SO24. The homomorphism between spin groups and special orthogonal groups relates to the fact that double-sided transformations are required to properly transform spinors. Since spin 2,4 is a simply connected Lie group, as I mentioned before, it is also the universal cover of SO24. So it's a double cover, a universal cover, it's a universal double cover. Now let's consider the fundamental subgroups of SO24 that make it so fascinating. So SO24, as we know, is the ADS5 isometry group, also called the space-time conformal group. Pretty important on its own. One subgroup of this, though, is SO14. That's the de Sitter four-dimensional isometry group, DS4. But we can also produce an ISO13, not just SO13 out of this. But that's the Poincare group. All of these groups immediately break down into SO13. That is, of course, the Lorentz group. And these are our fundamental space-time isometry groups for our consideration. considering that dimension 5 is as high as we want to consider for conformal purposes. Now let's have a short discussion on grand unified theory. The simplest grand unification Lie group for which we yield the gauge group of the standard model upon symmetry breaking is SU5. SU5 can be entirely embedded within the real representation of SO10. It is then a natural consideration to extend SO10 to its universal double cover for spinor representations, which is spin 10. The smallest exceptional Lie group containing our standard model gauge symmetries is E6, which incidentally contains SO10. We can then jump to the largest exceptional Lie group that contains everything we have mentioned and much more, which is E8. These larger groups contain potential windows to undiscovered phenomena, as they show potential gaps in the Noetherian symmetries of our theory. In M-theory, we can generalize to one of the two existing anomaly-free heterotic Lie groups in order to obtain quantum gravity and the standard model gauge group upon symmetry breaking. One group is given by the tensor product space composed by E8 with itself, and the other is yielded by SO32 alone. They are both 496-dimensional groups, though they are of different structure. However, that does not mean they are not profoundly related. The T-duality that links type 2A and 2B superstring theories also links E8 cross E8 to SO32, where T-duality implies that a string theory compactified on a circle of a given radius is equivalent to another string theory compactified on a circle with the inverse of that radius. Let's map that out to give us a journey from E8 cross E8 and SO32 to SU3 cross SU2 cross U1. So E8 cross E8, of course, immediately breaks down into E8, which, of course, we can go down from that to E7 down to E6. Now, let's also consider SO32 with a real representation. String theories compactified on these two, that's E8 cross E8 and SO32, are related via T-duality. Now SO32, we can go ahead and factor out an SO10 from it, because then we just have SO22 cross SO10. That's pretty simple math so far. Great. But SO22 cross SO10 and E6 immediately break down into the same group here. Not just from a duality, they both immediately break down into this group here, SO10 cross U1. So it's that U1 that has that complexification that added into that SO10 that brought our exceptional Lie group to such a similarity as our special orthogonal groups. And so now we know we can just extract an SO10 out of that to get our fundamental representation for which our universal double cover was spin 10. And then that breaks down, of course, into the unitary representations of SU5. So that's the smallest Lie group that contains G, which is SU3 cross SU2 cross U1, otherwise known as the standard model Yang-Mills Lie group. So this journey took us directly from dual 496-dimensional groups to the 12-dimensional group of the standard model of particle physics. Here is a projection of an E8 polytope onto 2D space with particles assigned to roots. Now we'll consider the canonical perturbative quantization of gravity, which will be an overview of linearized quantum gravity. When dealing with quantizing gravity, the first approach that may seem obvious is to quantize gravitational waves themselves. By doing this, we impose wave-particle duality on perturbations that occur in the metric, the perturbation being the extent to which we differ from a perfect Minkowski flat spacetime. So first we linearize the metric tensors in terms of the Minkowski tensor and the metric perturbation tensor. The free field Lagrangian in terms of the metric perturbation tensor is then given by the following. The gravitational wave equation for a classical vacuum state is then given by the D'Alembert operator acting on the perturbation tensor. Here's a simulation of two black holes colliding together, producing gravitational waves as they lose energy. We can promote the classical gravitational field to a quantum gravitational field perturbation by imposing a commutation relation in terms of canonical conjugate momenta. This will be given by the Kronecker delta function as well as the Dirac delta function acting in unison with the imaginary unit. This equation is the equation for quantum gravitational waves under the weak gravitational and linear limit. The quantized metric perturbation takes our original framework of rank 2 tensors, two forms or bivectors, however you might want to call them, and instead focuses on the massless spin 2 structure of the quantum fluctuations that arise under canonical momenta. These spin 2 fluctuations are called gravitons, though of course still hypothetical. You can see them added to the standard model on the very right as hypothetical tensor bosons. They will have spin 2, no charge. And when I say no charge, I'm also including mass, because in gravity, mass is the central charge. You can expand out the D'Alembert to see what this equation looks like in terms of the Minkowski metric tensor, which we see here. We're using a 1-3 signature, 1 negative and 3 positive. And we see we just get the sum of the negative acceleration derivative plus a Laplacian. And that's all this really is. Not much different from an electromagnetic wave equation when you really think about it, at least in a vacuum state. By replacing the metric tensor of the semi-classical Einstein field equation we discussed earlier with the metric perturbation tensor, we have an approximation of quantum gravity resulting from the energy densities formed by quantum fields. This is, as it currently stands, the closest we can get to a quote-unquote theory of everything when we follow Occam's razor and using only what we know so far about modern theoretical physics, in admission that this is not a final theory of everything by any means, but rather more or less a starting point. And then we can just expand that as follows to see its full form. That is our current best theory of quantum gravity, as far as we can say we almost know this much to be true. we still can't really work with quantum gravity at the Planck scale, and string theory and M theory, and all these things don't give us the full total answer of everything. But when we take everything we know from a pure mathematical standpoint and say, hey, we can actually do some calculations with this, and the quantum approximation is sufficient enough that we can actually even get classical theory right out of it, this is the equation you end up with. When the traditional metric is replaced with the quantized perturbation metric, we see that quantum fields alone generate an entire spacetime with weak gravity. In other words, these quantum fields, in a very weird sense, can predate an actual formal spacetime. That is to say, an entire universe itself can theoretically emerge from a spontaneous vacuum fluctuation obeying a Yang-Mills gauge symmetry, if even only for a moment among infinity. The full quantization of gravity is still an open problem that has bothered physicists essentially ever since general relativity was published and studied. While this is still very much a concern of physicists today, it is perhaps an artifact or either perhaps embellishment itself and miscommunication that we are convinced that there are no methods whatsoever of working with quantum gravity, as we certainly seem to be able to directly work with it in the weak field limit, really without any issues whatsoever. A controversial and perhaps uncomfortable fact is that although we still have issues working with quantum gravity at the Planck scale, we can approximate quantum gravity to essentially the same degree that Newtonian physics approximates general relativity. While in terms of physics, this is not remotely acceptable as a true theory of everything, it still manages to far exceed the hypocertainty requirements found in fields that determine law, models of psychology, politics, socioeconomic doctrine, social concepts of common sense from which your life will be determined if you disagree, anthropology, history, and many other fields of science or everyday life that many people take for granted or don't question whatsoever. These just good enough approximations, which are horrible in terms of physics, are models that occur often in fields of science where we are engaging in frontiers. Despite their complete and utter lack of completion, they often yield new technologies upon critical study, so studying equations like the one I have shown is likely a useful, though admittedly unpredictable, and perhaps extremely difficult endeavor. But discoveries in pure mathematics and other seemingly unrelated fields of science nonetheless are already occurring as we speak due to this. Here's a plot of the objects in the universe showing the Planck scale as a point where quantum theory and general relativity intersect. This is from Beggs and Majid's amazing book on quantum Riemannian geometry. So you see on the very left you have a particle event horizon for elementary particles for which we can define their existence in a space-time, and then the event horizons for which we define black holes and the masses of everything that exists in between them, such as a virus, a human, the scale of the Earth, the scale of Sagittarius A star, which is the black hole in the center of the Milky Way. And so that's exactly on that line that's called a black hole there. And so on that line past that black hole, we have the forbidden area of general relativity. On the line past the particle horizon is the forbidden area of quantum mechanics. The Planck scale is the point at which quantum theory and general relativity's event horizons, a particle and a black hole, are the exact same thing, in which you have nothing but spin, nothing but mass, and nothing but charge. You have three things that determine both things, and at that point you call that the Planck scale. So the Planck scale is not just the fundamental limit at which things no longer make sense when you go smaller, it's the fundamental limit at which all things are actually the same thing. And so therefore you have infinite uncertainty about what you're measuring. At the Planck scale, the quantum spacetime hypothesis expresses that a particle is indistinguishable from a Planck mass black hole. In other words, you have no clue what could possibly happen, really. In a sense, the combination of all fields at the beginning of an expanding spacetime are condensed into what's called a Planck particle at the beginning of time, which is a black hole that compactifies all known forces of fields into the density of a Planck volume. This further influences studies into how a universe can emerge from quantum fluctuations, especially if spontaneous symmetry breaking occurs. You imagine gravity would be probably the first to break. The study of physics on these scales is an active area of intense research, of course. Now let's consider the energy-momentum tensor for the graviton itself. We can consider a general form of the graviton energy-momentum tensor, though an exact representation does not as of yet exist. A full understanding of quantum gravity will require us to further understand an equation satisfying the following Yang-Mills structure. We see tensors related to the derivatives of the graviton field, but as it stands, neither string theory, M theory, nor loop quantum gravity or what have you provide direct, satisfactory answers as to what any of these tensors actually are. Nonetheless, here's our best equation in terms of quantum gravity. It states something fascinating. It expresses a model where quantum fields of matter induce space-time curvature, and space-time curvature dictates the evolution of the quantum fields. Another result from this equation is that while quantum field fluctuations do indeed curve space-time, spontaneous fluctuations of curvature caused by the graviton field is what endows a space-time with all the other non-graviton matter in the first place, because the graviton is the first to split in the symmetry breaking as the universe expands and cools. So instead of matter telling space-time how to curve and space-time telling matter how to evolve, in addition to that knowledge we just said with that equation, we now have a more fundamental structure suggesting that space-time and quantum fields mutually dictate one another without priority. Either of them can actually exist prior to the other, neither at the same time or both at the same time. That's not the point. The point is that quantum fields and space-times existing are mutually dependent at a scale at which you define gravity, curvature, all these dynamics that are occurring in our universe that are unique from pretty much nothing happening. Now let's consider the Stokes-Cartan theorem. It's worth considering an equation we ought to bet is related to everything mentioned, and it happens to be one of my favorite equations of all time. It is the generalized fundamental theorem of calculus in n dimensions, and it is formally referred to as the Stokes-Cartan theorem. Let omega be a differential n-1 form, where n is the dimension of a compact differentiable manifold M, and let d be the exterior derivative. The Stokes-Cartan theorem tells us the following. It tells us that the boundary integral of the differential n-1 form is equal to the actual integral over the whole manifold of the exterior derivative of that differential form. So it relates a differential n-1 form to an integral of a differential n form via a boundary to a bulk. This in and of itself is similar to what ADS CFT correspondence tells us, but just way more general. We can go ahead and derive the Stokes-Cartan theorem. We rely on the fundamental theorem of calculus in any finite dimension to derive the Stokes-Cartan theorem normally. But since we have already seen the divergence and curl theorems, we will instead rely on Green's theorem, which is the fundamental theorem of calculus for line integrals in 2 dimensions. On the left-hand side, we see a differential 1 form, while on the right-hand side, we see a differential 2 form. This pattern of differential n forms being related to differential n+1 forms continues across all fundamental theorems, and is in fact the pattern that ultimately defines and yields power to the generalized fundamental theorem of calculus. So let's set omega equal to a dx plus b dy. And now let's take its exterior derivative. Since these are anti-commutative, the only thing equal to its own negation is of course 0. So dx wedged dx must be 0, and so too is dy wedged dy. Let's bring our dx wedged dy to the front, and then switch that dx around on that derivative of a in respect to y. We pick up a negative sign when we change that dy dx to a dx dy. And then of course we can just organize. By now it should look pretty obvious what we just pulled off. Our equation can be written as follows. In this case, we're in R2, where omega is a differential 1 form and its exterior derivative is a differential 2 form. How about in R3? Well, in that case, omega is just a differential 2 form already, and its exterior derivative is a differential 3 form. So in R1, we obtain the original fundamental theorem of calculus, rewritten here in terms of differential forms. In R1, omega is a differential 0 form, also called a function. And so its exterior derivative is called a differential 1 form, also called the differential. The exterior derivative is nilpotent. So the exterior derivative of the exterior derivative is 0, since there is no exterior to the boundary already. In algebraic topology, this is of course equivalent to applying the boundary operator to another boundary operator. It must equal 0 since there can be no further boundary to something that's already defined as the boundary within a given dimension. A direct consequence is that the exterior derivatives are trivial elements of the kth singular cohomology group, H upper K of M and R. Perhaps even more interesting is the following isomorphism. We no longer look at differentials under this arbitrary notion of infinitesimals, as we have a much more rigorous understanding of them made available to us by viewing them as differential n-forms, where 0 forms are functions, or perhaps more abstractly by the isomorphism above, by viewing them as trivial elements of the singular cohomology group and therefore, due to the isomorphism, the D-Ram cohomology group and associated singular homology group. This is a Poincare duality, showing that cohomological dimensions are inversely linked with homological dimensions when orientation is considered. In this framework, all local properties of calculus can be summed up by a unification of algebraic topology and differential geometry. This is achieved by acknowledging the simple fact that the derivative is the opposite of the boundary of integration itself, as opposed to being the opposite of the entire integral. There's a reason, after all, we don't immediately eliminate indefinite integrals with derivatives and get to cheat and make A's in Calc 1. The universal coefficient theorem allows us to express the relationship between the homology of a space and its cohomology. This can be used to determine which groups correspond to one another. Let G, for example, be an abelian coefficient group, meaning we're dealing with symmetries of commutativity, and allow Hom and Ext to represent homomorphism and extension functors, respectively. Hom of H sub k of M and G is the homomorphism group from the kth singular homology group to the abelian coefficient group. The cohomological universal coefficient theorem can then be expressed as follows. We have a direct sum of the homomorphism and extension functor groups. When we utilize the group of real or complex numbers, which are also abelian groups, torsion vanishes since there are no non-trivial extensions of algebraic fields in terms of this extension functor. The cohomological and homological universal coefficient theorems simplify to the following when G is an abelian algebraic field. We'll use the complex number c for this example. We see here the functional Stokes-Cartan theorem emerging from semi-classical field theory. We consider the Feynman path integral for the combined Einstein-Hilbert and standard model Lagrangian action in terms of a functional measure over all fields d of g, phi, and psi. When varying the action S around the boundaries of the integration domain, we obtain a functional generalization of the Stokes-Cartan theorem in terms of first-order variation of the stationary action. So we have a bulk term with a boundary term, defining the stationary action being acted on by the functional derivative. We know the variation must go to 0, meaning we also know what the sum of integrals evaluates to. This yields the functional Stokes-Cartan theorem, which generalizes the fundamental theorem of calculus to infinite dimensions. This one expression contains the entirety of calculus under the unification of algebraic topology, differential geometry, and functional analysis. Now let's consider the de Rham complex. Now that we have the local and non-local properties of physics integrated under functional n-forms, it would appear that all of physics comes down to a unification between the trivial and non-trivial elements of the de Rham complex. Differential n-forms compose the trivial elements of that complex, yielding local properties of physics. By extending to covariant and/or functional differentiation, however, we compose the non-trivial elements of the de Rham complex, yielding non-local or global properties of physics. The nth de Rham complex chain is given by the following. The kth de Rham cohomology group can then be defined as a quotient of a kernel of the exterior derivative acting on k forms by an image of the exterior derivative acting on k minus 1 forms. In R3, the de Rham complex yields the following map. And we go from smooth function spaces from 0, 1, 2, and 3. We're just defining gradient, curl, and divergence. And so that's where the fundamental theorems of calculus really start to come from. Now let's extend this to complex differential geometry. If we allow our forms to take complex values in the case of holomorphic manifolds, then we can decompose the exterior derivative of a complex PQ form, zeta, into a sum of complex analytic and non-analytic derivatives called the holomorphic and anti-holomorphic Dolbeault operators, respectively. The nilpotency of the exterior derivative can now be written as follows. This allows us to define the Dolbeault Laplacians on complex manifolds. The Hodge Laplacian, or the true, full geometric Laplacian, can then be written in terms of the holomorphic and anti-holomorphic Dolbeault operators. We can expand the terms and express the operator acting on zeta. Note that zeta can be decomposed into a sum of harmonic, exact, and coexact forms. This is called Hodge decomposition. We are in a position to formulate the Stokes-Cartan theorem as a fundamental theorem of complex analysis. However, as we have seen before, the sum of holomorphic and anti-holomorphic derivatives simply yields the exterior derivative. Since it's acting on zeta, it turns out that even the theorems of complex analysis are limiting cases of the Stokes-Cartan theorem. Recall the kth DRAM cohomology group once again. We now have analogous holomorphic and anti-holomorphic cohomology groups called the Dolbeault cohomology groups. We can compose these with the exterior derivative to form a Dolbeault double complex. The convergence of Dolbeault cohomology to DRAM cohomology is called the Hodge-DRAM spectral sequence. This holds for Color manifolds in general, but there is one in particular we will consider. We will consider a Ricci flat, compact Color space, ideal for minimal energy conditions, called a Calabi-Yau manifold. For color spaces such as these, we find a fascinating Hodge decomposition. It turns out that the sum over all P and Q of the anti-holomorphic variation of this sector is isomorphic to the kth DRAM cohomology group of N. Now let's finish up with non-commutative Stokes-Cartan theory, which I like to consider the fundamental theory of modern geometry. While a formal construction of non-commutative differential geometry would exceed a reasonable allotment of time for this presentation, we can conceptualize it just fine by essentially forgetting everything we think we understand about mathematics as a whole. Consider the following spectral triple: A, H, and D. A can be a C-star algebra, W-star algebra, or a more general Banach operator algebra. H is a Fock space or related Hilbert space. And D is the Dirac operator, generalizing derivatives to a derivation operator. Since integration is replaced by the trace of operators, the Stokes-Cartan theorem takes a more general form in respect to the previously defined spectral triple, and now we have a non-commutative and algebraic equation. By letting gamma be a grading operator, we now write the Stokes-Cartan theorem as follows. The trace of this grading operator acting on the Dirac operator is equal to the boundary term. The Stokes-Cartan theorem can be interpreted as measuring the extent to which commutativity fails for a given mathematical structure by a boundary theory. The extent to which commutativity does not fail is the limit at which we approach the standard fundamental theorems of calculus and a lot of the math that we know in the first place. This means that space-time dynamics as well can be extrapolated as a byproduct of a non-commutative geometry, in which notions of space-time itself are unnecessary to describe phenomena. This is much like how the jump to tensor calculus allowed us to express coordinate invariant physics. This all seems to apply that if we are to ask questions like, what happened before the Big Bang, we will likely need to begin thinking of generalizing space-time itself. This is not simply arguing for a multiverse or a metaverse. This is a mathematical structure that would be more fundamental and could explain not only the nonlinear dynamics of our universe, but also how it and potentially others may arise from pre-geometric states altogether. It is worth noting, however, that the calculations involved at this stage are among the most challenging problems in both physics and modern mathematics as a whole. Let's go over the groups and algebras we have covered. In this video, we've been enamored with mathematically rich structures that underpin everything we currently know about in physics in one way or another. Of course, we have our special unitary groups and unitary group. Then we have the Lie cross product as well as the direct sum. Then we have the orthogonal, special orthogonal, and spin groups. Then, of course, we have our Fock spaces, composed of tensor product spaces and exterior product spaces, respectively. And, of course, we have our Clifford algebras. And then we have our homology and cohomology groups. And finally, we have cross-product groups such as EA cross E8, which will compose our exceptional Lie groups such as E8, E7, E6, and so on. And I'll leave you with a couple of questions that keep me up at night. 1. If spin 2,4 is the universal double cover of SO2,4, then it contains two copies of SO1,4 and ISO1,3. Is it possible that conformal symmetry breaking could change an ADS vacuum to a DS spacetime with matter? Two, similar to the Higgs mechanism, is it possible that a vacuum obeying SO2,4 symmetry can experience spontaneous symmetry breaking and reduce its isometries to the Poincare and Lorentz groups, thus endowing a spacetime with fundamental charges? And 3. Will the holographic principles that arise from the studies of conformal isometry groups in homology/cohomology lay the fundamental groundwork relating spacetime dynamics as a whole to cosmological and/or black hole event horizons, perhaps even leading to an effective theory of quantum gravity? And then, of course, the ultimate question, number 4. Why is the following cat so cute? Thanks for watching.